Hi, my name is Justine Harkness, and in this video, we'll look at how to use the resistivity formula to calculate the resistance. Resistors are components of circuits that dissipate energy and also slow the flow of current. And we measure the resistance of a resistor based on how much it impedes the flow of the current. The unit for resistance is the ohm. Now let's take a look at some of the properties that affect the resistance of a resistor. And it all comes down to this formula. So we're looking at R, which is the resistance of our resistor, and it depends on several physical properties of the resistor. The first one is ρ, which is the resistivity. This is an intrinsic property of the material from which the resistor is made. So the greater the resistivity of the material, the greater it inherently impedes the flow of current. For example, if you look at the wiring in a house, all of the wires are typically made of copper. Copper has a very low resistivity, which means it doesn't impede the flow of current very much, which makes it a perfect material for transporting current throughout the house without causing electrical fires. We also have the length of the resistor, just essentially how long it is, measured in meters, and then the cross-sectional area, measured in meters squared. Now, if we take a look at some of the relationships between these variables, which is something I love to do whenever I am analyzing a new formula, we see that the resistance is essentially directly proportional to the resistivity. The resistance is directly proportional to the length, meaning the greater the resistivity, the greater the length, the larger the overall resistance. We also see that the resistance is inversely proportional to the area, meaning the greater the cross-sectional area, the lower the resistance of the resistor. And in general, the resistance also increases with increased temperature. Now, in terms of the temperature, it's really the resistivity value itself that is temperature dependent. So if we're given a resistivity value for a particular material, we can assume it's for the temperature that the circuit is at, so we won't really need to adjust for the temperature specifically when we're doing our calculations. So let's take a look at some practice questions. So this question tells us that household electrical wiring is most commonly done using 12 gauge copper wire, which has a diameter of 2.05 millimeters. Now we also have a note here telling us that the copper wire is coated with an insulative material to prevent electrical fires, which is good. And we are given the resistivity of copper as 1.68 times 10 to the negative 8 ohms meter. Now, we have to look at our resistivity formula. We have rho L over A, and we're given here the resistance of a 20-meter span, so we know the length. We have the resistivity here, 1.68 times 10 to the negative 8. The last thing we need to figure out is the area, and we can do that from the diameter. Now remember that the area is equal to pi r squared, and since we are given diameter, we would need to divide this by 2 to get the radius and then plug that into our equation for r. Also note that all of our units here are in meters, so we would need to convert that, which would now be 1.025 into meters. So that's why we have 1.025 times 10 to the negative 3 meters. And when we crunch the numbers, we'll get our cross-sectional area of 3.3 times 10 to the negative 6 meters squared. And now we can plug in all of our values into the resistivity formula. We have our resistivity of the copper, we have the length of the wire, and then we have the cross-sectional area. And this would give us a total resistance of 0.1 ohms. Next, we're making some changes to our wire. So B asks us, how would the resistance change if we use 6 gauge copper wire, which has a diameter of 4.1 millimeters? Now notice what we have done. We've gone from 2.05 millimeters from what we used in part A to 4.1. So we've essentially doubled the diameter. Now, if we think about the area being pi r squared, if we double the diameter, that's the same as doubling the radius, which would give us 4 times the area. So area is 4 times larger. And now let's look at the relationship in our formula. So resistance is inversely proportional to the area. So if we were to increase our area by a factor of 4, the resistance should be decreased by a factor of 4. So we'll take that 0.1 ohms and we'll divide it by 4. So our new resistance would be 0.025 ohms. Now C asks us how the resistance would change if the span was increased to 60 meters. So originally our length was 20 meters. To get it to 60, we have increased it by 3 times. We know that the resistance is directly proportional to the length. So if we increase the length 3 times, we will also triple the resistance. So here our resistance would be 3 times larger, which would be 0.3 ohms. So now you should feel more comfortable using the resistivity formula to calculate the resistance and working with the relationships between the variables in that resistivity formula.